Thank you for introduction. I'm really have a pleasure and honor to be with you even online. So many thanks to organizers that let it possible. And I will talk also about this very interesting object, what is called a SIC-POVM. And it's based on a paper with my colleague Wasyl Ostrowski, and this paper is published in Letters in Mathematical Physics journal. It's in this year. Okay, I'll briefly try to briefly reintroduce the basic notions. We work in a finite-dimensional complex Hilbert space, and there is a notion of Yakymenko tight frame, right? So it's n unit vectors, and the Yakymenko error, so modulus of inner products are constant, and there is a tight condition, right? So projectors, sum of projectors is a scalar operator, or equivalently we can write that this is so-called a frame operator is scalar matrix. And this F is a what is called frame synthesis operator, where we just put those vectors as vector columns in this matrix. All right, and as was mentioned by Professor Ingemar, this is possible only if n in this interval, and if n is equal d, then this is just an orthonormal basis. And if n equals d squared, then this is so-called a maximal ETF, but only if it exists, right? And in this case, we know the angle. Actually, we always know the angle. Angle is just determined from n and d. Okay. And another name for those maximal ETF, it's SIC-POVM, or just SIC, right? So this is a symmetric information or complete positive operator measure. It says because those operators form, their sum is just an identity, right? They form a measure. And there is a well-known Zonor's conjecture. The weak form of it is that 6 exists in any dimension. All right, there is already very large evidence that supports this conjecture. Right, and another interesting, which is also determining property of 6, is that they are in fact what is called minimal complex projective two designs. What does this mean? A complex projective two design is a set of unit vectors such that the following holds, where this is assume just a sum of tensor squares of projectors, right? And this is a projector on a symmetric subspace of H tensor H. Symmetric subspace is can be defined just a linear span of simple symmetric tensors of this form. We know this its dimension, right? It's like close to the half dimension of the whole space. And this equation actually means that, this projector is actually an average, roughly speaking, it's an average of all such projectors. Strictly speaking, we can we should write an integral over complex projector space under the measure that comes from Haar measure, right? And it is known that it must be that n is at least d squared, right? And another important fact that to design is also always a one design, which is just the same thing as tight frame. And another interesting fact is that we can actually bound n from above, because there is always a to design with such n, at least such n, for any dimension d, right? And it turns out that that a SIC is that a frame is SIC if and only if it's also a projective to design. So SIC is optimal from some other viewpoint, right? So this is why it's so interesting object. Okay. Now note the following. From the definition of to design, we can see that tensor squares of vectors that form of these vectors, they actually form a tight frame on the symmetric subspace, right? It's, well, we can just back for a moment, right? Because this is it's just a projector on the VI ket VI tensor ket VI, right? And this is just an identity on the symmetric subspace. Okay. So we can view it as a tight frame on the symmetric subspace, right? And once we have a SIC, then their tensor squares, all those vectors, this means that they form an equiangular tight frame of this type, right? So d-squared elements in this dimension. And now let's look at the following property. We can, for a time frame, we can take a Gram matrix of a tight frame, which can be written as this this formula. And if frame is tight, then we know exactly what is spectrum of the Gram matrix, right? Now, the spectrum of Gram matrix, it's just the same spectrum of the frame operator, which is, I recall, for a tight frame, it's scalar, right? And some zeros. Well, it's actually always true when we just flip the product of two matrices. All right, so we know exactly the spectrum of Gram matrix. Now what we do, we can take let's call it G2. It's a Gram matrix of tensor squares, of SIC tensor squares, right? So in other words, it's just Hadamard product of 2 gram matrices or just a SIC, right? Now, what we see is that this G2 gram matrix, it has a unit diagonal. Of the diagonal entries, all have modulus alpha squared, right? And the spectrum of this matrix we calculate from this proposition, and we know it completely. Yes, it has 2 points with this multiplicities, right? Now what we can do, we just take this linear transformation of this matrix, of this gram matrix. It's and it turns out that it's not easy to see. It is easy to see that this will be a complex self-adjoint Hadamard matrix with unit diagonal, right? And this is how every SIC is actually related with some Hadamard matrix. Right, and two things to note. First of all, this is true not just for SICs, for SIC-POVMs, right? We can just start from any ETF of this type, and the same, and take just its gram matrix, because the modulus will be the same anyway. And the second thing to note is that this theorem actually goes the other way. So we can start from Hadamard matrix of this type, right? So it's self-adjoint with a unit diagonal, right? And for those matrices, we know exactly the spectrum of them, and so we can go backwards. And when we go backwards, we come to some equiangular tight frame of this type. But it is not always a SIC. It is rarely a SIC actually. Okay. And one more thing about the Hadamard matrices. Let's take the Fourier transform matrix. It's a without this factor, it is a well-known Hadamard matrix that exists in every dimension. And for this matrix, we can consider which I call sort of a skew-Kronecker product of a joint Fourier matrix and Fourier matrix. It can be defined by this way, where this is how I wrote this skew product. And you can think that this matrix is, well, it has size d squared times d squared, and you can think that it is a block matrix, right? And in the block IJ, we put this matrix, and this matrix is what is this part is that we take column, j's column of this matrix and multiply it by i's row of this matrix. And it's not hard to see that this total matrix, it just permutes entries of a usual Kronecker product of these two matrices. And it turns out that this construction is very interesting because it is self-adjoint and it has exactly unit diagonal, right? And consequently it gives rise to some ETF of this type. So it won't be related to a SIC. But we will see later why it is also interesting from another point of view. And another thing to note is that this is actually true not just for Fourier Hadamard matrix. We can put any Hadamard matrix here in this formula, and the same will be true. And this construction is actually even further generalized. We can put even parameters in this construction. So there is a multi-parameter family of equivalent frames of this type. Also, I didn't check if SIC frames that come from SIC are actually in this family. Well, this is an interesting question, but I generally don't believe in such a luck. Okay. Okay. Now, it is not hard to observe that when we have some equivalent tight frame of this type, right? Then if we embed it in a asymmetric in a symmetric subspace somehow, there is a choices how we can embed frame of this type. And if all vectors, when we embed it's in a symmetric subspace, when all the vectors are actually simple tensors, then it's just trivially follows that Vi should form a SIC, right? So we can say that every SIC come from an ETF of this type with this property. And there is a natural, we can introduce some natural measure of how far we from a SIC when we look at some ETF of this type, right? We just for a vector from a symmetric subspace, we can introduce the notion of its symmetric rank, right? Now, since for every symmetric vector, it's always a linear combination of simple symmetric tensors, right? And we define just symmetric rank as a minimum number S, so that this ket W it is a linear combination of just S simple tensors, where those are just complex numbers, those coefficients, right? And there is a actually interesting theorem that's, in fact, symmetric rank of a symmetric vector. It's just the same quantity as Schmidt rank of a vector, which is a known thing in quantum information theory. And moreover, for a symmetric vectors, there is always a symmetric Schmidt decomposition, right? This is a decomposition. It can be written, every symmetric vector can be written as a linear combination where this UI is just they are just orthogonal to each other and have unit norm. I actually didn't see this result in some common literature, so maybe it's, but I think it should be known to someone. Okay. 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 Now let's talk about group covariant 6. Yes, we have this omega, it's a root of unity, and tau, it's a root of unity, also root of unity. If dimension is even, then it's in root of power of 2D, right? We have this what is called clock and shift matrices, and we generate we can generate a group. We can define matrices from those. We can define these matrices that are called displacement or translation operators, and they have those nice relations between them, right? Okay, a bit faster, and they form what is called the Weyl-Eisenberg group, and this is actually, well, this definition is slightly different because here the center of this group is consists of powers of tau, but this is actually not a big difference with more usual definition, as was said by my previous speaker. Okay, we have this notion of covariant SIC, which we call just VH SIC, and which is constructed just from a single fiducial vector by action of these operators, displacement operators, right? And the strong form of this conjecture, then there exist in every dimension. VH6 exists in every dimension, right? Okay. And now let's look at our main observation. For every unit time frame, we can rescale the vectors so that they will form what is called a Parseval frame, right? So it's where the sum of these elements is just an identity. And there is a known Nymark theorem that says that every Parseval frame is actually unitary equivalent to a projection of some orthonormal basis into space, into some subspace of dimension D, right? It's easy to see this theorem in reverse implication, because once we take a basis, we have this equations, and once we take a projector, then when we project, we have this formula, and so projection of a basis is clearly a partial frame on the image of a projector, right? And now we recall that SIC squared is it's a ETF of this type on an H metric subspace. And so as a corollary of this theorem, Nymark theorem, there should be some basis of H, tensor H, such that the projection of this basis it is this squared SIC, right? Okay, and now what are the ideas of our work, right? What if first, can this basis have some additional nice structure? What if those bases, maybe they are somehow easier to describe than SIC itself? And can it some lead to something new that this discoveries? Those are just abstract ideas, right? And in particular, we will be interested about what we call just a Weil-Heisenberg group covariant basis, right? So just by analogy, we just define as a VH basis if it's an orthonormal basis of H, tensor H, that has this form, right? So it's just come from some fiducial basis vector, right? And by this BVH, we will denote the set of all possible fiducial vectors of all possible bases of this type. Okay, and the main result is that actually once we have any Weil-Heisenberg SIC, then there exists a fiducial basis vector such that this SIC is a projection of this fiducial basis vector, right? And since there is a commutation, when we project the basis, we just obtain exactly squared 6, up to a factor. This is the main result, and other results. It's that there is actually a complete description of those bases. We show that a particular basis is close in some structural, let's say in some structural sense, to a squared SIC. And we also show how the so-called generalized parity operator emerged here. Okay, first of all, let's see why this set is actually not empty. We can take the Fourier matrix, and then we just take tensor K0 F tensor, and so this element actually belongs to this set. It is because the conjugation by F, it exchanges Z and X matrices, right? And it then follows that when we look at the generated basis, it has this form, and this is clearly, and this set of elements is clearly form a basis in H times H, H tensor H. And here is actually, this basis already has some very surprising properties. Well, first of all, once we project this basis on symmetric subspace, then, well, we can think it will be a unit type frame, well, after normalization, and it also will be equiangular, right? There is not always true that when you take a projection that it will be an equiangular. Now, if you calculate the Schmidt rank of each vector, it's just 2. So it's just 1 rank away from a SIC-POVM. So it's, in some structural sense, it's somehow it's close, but it's hard to jump from this construction to 6. Just anyway, it's very hard. And lastly, when we compute the corresponding Hadamard matrix of this equiangular type frame, it will be exactly this this construction as we talked earlier, right? Under the natural ordering of pairs of that is our indices, right? So and that's why I think it's so interesting. Okay, let's talk about how we can describe the set of all this basis. It turns out that there is a related notions that help us describe them. We can consider unitaries on H tensor IH, that unitaries that can be written in this form. So they are just linear combination of displacement operators squared, right? And clearly they form a group under multiplication, and we will denote this group by this symbol. And one nice description is the following. Once we have two different fiducial basis vectors, then there is always a unitary such that a unitary from this group such that it transforms one fiducial vector to the other, and we can compute actually this unitary explicitly. And on the other hand, once we have fiducial basis vector and some unitary from this group, then the image is always a fiducial basis vector too, right? In other words, it's what's called that this group acts regularly on the set on this set. Okay, let's go further. Okay, let's look closer at this group. Well, it is actually a subset of algebra generated by these two operators, right? And this pair of operators, it satisfies this commutational relation. So it means that this pair it represents the abstract operator relation. In more strict words, we can consider the free. We can consider sister algebra generated by two free variables with this relation, right? And the representation theory of this relation, it's actually known. Where if we when this lambda is just a root of unity, and I prefer this. there is a different context. It appears in different books. I prefer this formulation, and it says that there is always for any two complex numbers there is a unique unitary representation in dimension Q such that we have this equation. It can be constructed by this way, right? Where those det and x matrices of size Q, right? So what we are going to do, we can apply this classification theorem. Well, any other representation is just a direct sum of irreducible representations. So we are going to apply this theorem to understand how to understand this pair, right? So this pair will be, by the general theory, this pair will be a direct sum of irreducible representations of this type, right? Okay. And well, let's call representation given by these two pairs as rho, and so that rho of A is just this Z under Z, and rho B is this, right? And if dimension is odd, then omega squared is still root of order root of 1 of order G, right? And so every irreducible representation will be in dimension D, and we can check we can look at the spectrum of these powers to conclude that this representation rho is just a direct sum of P11 as defined in the theorem, right? We can actually put it explicitly what is P11 in this case. And if dimension D, but if dimension D is even, then omega squared is actually primitive root of 5 of order D over 2, and so every irreducible representation will be in this dimension. And to apply this the previous theorem, we need to look at this spectrum to see what are possible values of alpha and beta, and there will be 4 choices. And in fact, it can be proved that in this case, this representations rho, it's this direct sum. So for every possible choice of alpha and beta, we have this. They appear exactly the same number of times, D over 2. Right? And this is why even odd and even cases are so different, and this even case is, in some sense, it's a little bit harder. Okay. Now, let's specify to the case when it is odd. The dimension is odd. Since the representation is a direct sum, then we can take some explicit decomposition into the invariant subspaces. And moreover, we can put it in a way that symmetric subspace is a direct sum of, let's say, the first D plus 1 over 2 invariants in places, and asymmetric, which is a complement of symmetric space, is the other, sum of the other. Now we can from what we deduced, we can write that the representations on the component, on the ice component, is exactly it's actually equals the representations on the zero component under some isometry, where this under some this isometry can be explicitly computed from the decomposition. And finally, we can formulate the description of this. First, we formulate the description of this group. So this is very easy. Once we have just some operator, then it belongs to this group, if and only if, let's say, the restriction on the zero component is unitary, and the restriction on other components are just related under this isometries that are computed from the composition, right? And we can give a description of the basis. We can denote as pi projectors on those parts, right? Yes, and there is a theorem that unit vector B it belongs to this set of fiducial vectors if and only if the set that we can compute from it is actually an orthonormal basis. We compute this part, this bi0. What we do, we just project this fiducial vector B first on the component hi, and then just send it to the zero component by using our isometries. Or on the other, in the other nodes, we can formulate it in a different way. We can say that we just take some orthonormal basis on the component H0, and then we just form this fiducial basis vector in this way, right? We take element of this basis and send them to the corresponding part, to the corresponding invariant part, right? And this is a description, and we can there is a related technical lemma that helps us prove our main theorem. And this lemma says that once we have a SIC fiducial vector, and once we form this vectors, right? So we project this squared fiducial on the i's part, and then send them to the i's to the zero, right? Then those vectors will be mutually orthogonal and have norm 1. So to prove the main theorem, we just need to. The idea is just we then can complete this set of vectors right to the full basis, and that's all. Okay. Next. one more thing. It is a notion of generalized parity operator. We can it exists for any SIC. Once we have a SIC, we can define the phases that corresponds to angles between vectors of SIC, and we can algebraically define this operator, which will be a reflection with trace 1, so that it's self-adjoint, and square it. If you square it, then this will be additive. This operator plays actually an interesting role. It plays an important role in the construction of ladders that was mentioned by Professor Ingemar in the previous talk. So we can see how it emerges geometrically. We can take, since it is a reflection, we can take this. We can define the corresponding projection that come from this and this projection. This projector will have this rank d+1/2, and it turned out that under a natural isometry between h0 and h, it just follows that it is a sum. This projector, it is a sum of projector on those vectors that form a non-complete basis. Say, I'll say it this way, and this basis is what we defined in this previous slide. So it is, in some sense, it gives it some geometrical meaning. Okay, I can just say one more thing, that it can be simplified in some way, but I think I'm out of time, so I will not. And last thing I want to say that we can try to use this set of bases as a search space for all solutions. And what we just can seek when we take fiducial basis phasors, fiducial basis vector, we seek the condition that Schmidt's rank of the projection is just 1. And computationally, this means that we can try to maximize the purity function of the partial trace of the corresponding density, almost density matrix, right? But in fact, I'll try this way, but without some heuristics, this approach, unfortunately, not very efficient for finding numerical solutions, so I can't represent some additional, some new constructions, but I believe, anyway, this way is promising. Okay, and thank you.